How do magnetic levitation trains work? Welcome to today's video. Have you ever wondered how trains can float above the tracks, almost like they are gliding on air? This futuristic technology is called magnetic levitation, or Maglev for short. In this video, we'll dive into the fascinating world of maglev trains, explain how they work, and discover why they are considered the future of high-speed transportation. What is magnetic levitation? Magnetic levitation is a method of transportation that uses powerful magnets to lift, propel, and guide a train along a track without making contact with the rails. Imagine that. No friction, no wheels, just smooth, silent motion. But how exactly does this work? Maglev trains rely on two sets of magnets. One set repels the train upward, lifting it off the track, while the other set pushes and pulls the train forward along the guideway. This combination allows the train to travel at incredibly high speeds with very little resistance. Most maglev systems can reach speeds of over 300 miles per hour, or 480 kilometers per hour. How does levitation happen? The key principle behind maglev trains is electromagnetic suspension. Large electromagnets are installed along the track, and the train itself is equipped with superconducting magnets. When electricity is applied to the system, it creates a magnetic field that lifts the train off the track by about 10 millimeters. While this may seem like a small distance, it's enough to prevent physical contact and eliminate friction entirely. Additionally, the electromagnetic force stabilizes the train in midair, ensuring a smooth ride. This means that the train can levitate and move forward without touching the tracks, creating an ultra-efficient transportation system. Propulsion and movement. Now, you might be asking, if the train is floating, how does it actually move? Maglev trains use a method called linear induction motors. Instead of relying on conventional engines, linear motors create a magnetic wave that propels the train forward. The train is essentially being pulled forward by magnetic attraction and pushed by magnetic repulsion. This process allows maglev trains to accelerate quickly and brake smoothly, without the need for friction-based wheels. The maglev train developed by Central Japan Rail and Company is currently the most advanced in the world. Let's take a closer look. This train uses superconducting magnets, which is why it's called the SC maglev. Once charged with an excitation electric current, the superconducting magnets generate a circulating electric current and a powerful external magnetic field with zero energy loss. Let's explore this successfully tested technology further. To successfully operate a maglev train, all three objectives must be achieved. 1. Propulsion. 2. Levitation. 3. Guidance. In the image, we see a unit of 4 superconductors with opposite electric current polarities. The superconductors are made from a niobium titanium alloy with a critical temperature of 9.2 Kelvin. These cooling units keep the alloy's temperature below this critical limit. They are attached along both sides of the train. For propulsion, normal electromagnets, called propulsion coils, are placed inside a base. To understand the direction of the force one magnet exerts on another, you only need to consider the nearest poles. By analyzing the force acting on the superconducting coils caused by the propulsion coils and observing the outcome of all these forces, the resultant force will point forward. This means the train will move in the same direction. Once the train reaches the next midpoint, the propulsion coils switch to an alternating polarity, so the resultant force is once again directed forward, keeping the train moving in the same direction. By controlling the frequency of this switching, you can control the train speed. In the levitation of SC Maglev trains, you'll be surprised to learn that levitation is achieved using these simple figure-8-shaped coils arranged along the guideway. To better understand levitation, we must first learn about the nature of a pair of superconducting magnets. The resultant magnetic field produced by this pair of superconducting magnets is very similar to that of a long permanent magnet. So, to simplify the analysis, let's replace them with a long magnetic bar. If a magnetic bar moves parallel to these figure-8 coils, what can we predict will happen? The changing magnetic flux will induce an electric current in both loops. According to Faraday's law, are these electromagnetic fields in the same direction? Notice that this is a coil twisted into a figure-8 shape. Only when we untwist it can we understand the correct direction. However, the resulting value of the magnet's movement at the center of the loop is 0. To achieve levitation, we need to shift the magnet slightly downward within the loop. In this situation, the lower loop will encounter a stronger magnetic flux. This means the electromagnetic field induced in the lower loop will be greater than in the upper loop. This stronger force causes a resulting current to flow through the circuit. This flow creates an internal south pole in the upper loop and an internal north pole in the lower loop. By analyzing the interaction of forces between these magnetic poles, an upward force is applied to the superconducting magnet. If this resulting force is stronger than the force of gravity, the magnet will move upward. In other words, the movement of a superconducting magnet, parallel and slightly offset from a figure-8 coil, will produce levitation. As the superconducting magnet moves upward, the difference between the values of the electromagnetic field and the current flow in the loop decreases. This means the force in the loop also decreases, and when the upward force equals the gravitational pull, the superconducting magnet reaches equilibrium. In other words, levitation. The faster the train goes, the stronger the levitation force becomes. But when the train is stationary, it can't levitate. That's why Maglev trains use regular tires for starting and for operations at low speeds. Once the train reaches a certain speed, the tires retract because the electromagnetic force has become strong enough to lift the train. Orientation means the train must always stay centered, moving without hitting the sidewalls. It needs to have lateral stability. Japanese engineers achieved this by interconnecting the same figure-8-shaped coils. The electromagnetic fields in the right and left coils balance each other, and no current flows through the interconnecting coils, keeping the train in the center. However, unexpected events can occur. If the train moves slightly to the right, this shift will disrupt the balance of the electromagnetic fields between the left and right coils, causing current to flow through the interconnecting coils. This current affects the magnetic force in the lower loops, altering the strength of the poles in each loop. When analyzed, the vertical force remains the same, but a horizontal force pushes the train back to the center. As it moves closer to the center, the current decreases, and the horizontal force disappears, restoring stability. An incredible mechanism to maintain orientation stability. After understanding all the workings behind Maglev train technology, we need to know what its advantages are. There are several reasons why Maglev trains are being hailed as the future of transportation. 1. Speed. Since there's no friction between the train and the track, Maglev trains can reach incredibly high speeds, often faster than airplanes on short routes. 2. Efficiency. With no wheels touching the rails, there's significantly less wear and tear, meaning maintenance costs are lower. 3. Quiet. Maglev trains are much quieter than traditional trains since there's no clattering of wheels on rails. This makes them ideal for urban environments. 4. Sustainability. Many Maglev systems run on clean energy, such as electricity from renewable sources, reducing the environmental impact of high-speed travel. What are the limitations and challenges faced by maglev trains? However, while maglev trains sound perfect, there are still some limitations that prevent widespread use. One of the main challenges is the cost. Building a maglev system is extremely expensive, particularly the tracks, which need to be equipped with precise electromagnets along the entire route. Additionally, because maglev technology is relatively new, it requires a lot of research and development. Not every country can afford to invest in this technology yet. At the moment, which countries have maglev trains in operation? In Japan, commercial SC maglev trains are authorized to operate until 2027 between the cities of Tokyo and Nagoya. A project is underway to connect New York City to Washington, D.C. in under 1 hour by 2030. A commercial flight between the two cities takes an average of 1 hour and 24 minutes. Japan is notable for having tested superconducting maglev trains, which differ from Shanghai's electromagnetic suspension-based system. In China, the Shanghai maglev train was indeed the first commercial maglev line in the world, launched in 2004. This train uses German Transrapid technology and operates between Shanghai's Pudong International Airport and Longyang Road at speeds reaching up to 431 km per hour. At the beginning of this year, 2024, China initiated studies for the creation of the country's first Hyperloop railway line. This high-speed train model aims to reach speeds of up to 1,000 km per hour. According to the local government, the vehicle is expected to connect the cities of Shanghai and Hangzhou via a 150 km long vacuum tunnel. The line is projected to begin operation in 2035. Several projects featuring new models of high-speed trains are set to continue developing this mode of transport in the coming years. At the beginning of this year, for example, the Netherlands inaugurated the first European test center for superfast trains on the continent. As of now, there are 6 operational commercial maglev lines, all located in Asia, China, Japan, and South Korea. However, Germany does not have an operational maglev system, despite its early development efforts. Japan and Germany are the countries that have conducted the most research into this technology. What is the future of maglev? As technology improves and costs decrease, we can expect to see more maglev trains around the world. They could transform how we think about long-distance travel, making it faster, more efficient, and better for the environment. Imagine a future where you can travel between cities in minutes rather than hours, all thanks to the power of magnetic levitation. And there you have it, a deep dive into how maglev trains work. From electromagnetic levitation to high-speed travel, maglev technology is poised to revolutionize transportation as we know it. If you found this video interesting, make sure to hit the like button and subscribe for more fascinating insights into the world of technology and transportation. Thanks for watching, and we'll see you in the next video.